Hey everyone, today we're going to be talking about the Pythagorean Theorem. So we'll go ahead and begin with a right triangle. We're going to label the sides A, B, and C, where A and B are the sides that are adjacent to my right angle, and C is going to be my side that sits opposite the right angle. C is incidentally the longest side of the triangle, and we give it a special name. We call it the hypotenuse. So whenever you hear the word hypotenuse, it refers to the longest side of a right triangle, and this is always the side that sits across from the right angle. Now, since I have a right triangle, the idea is I then know how the sides A, B, and C relate to one another. Triangles can be pretty complex, but when I know that there's a right angle that exists in the triangle, I get more structure, and I get more rules that I can follow. The most powerful rule that we use is called the Pythagorean Theorem, and it says that if I have a right triangle with sides labeled A, B, and C, where C is my hypotenuse, then A squared plus B squared is equal to C squared. So the main idea is that if I have a right triangle and I have information about two of the sides, then I can always solve to get information about the third side. Let's go ahead and talk about how to use it in some problems. In the following triangle, find the length of the hypotenuse. We'll go ahead and label the hypotenuse with C, so it agrees with our formula. And I'll also call the sides 4 and 5 A and B respectively. It doesn't matter which side I labeled A and which one I labeled B, as long as it's not the hypotenuse. They just act as placeholders so that I can use the formula from the Pythagorean theorem a bit more efficiently. The Pythagorean theorem says that C squared is equal to A squared plus B squared, but since I know what A and B are, I can substitute that information in to get that C squared is equal to 4 squared plus 5 squared, which simplifies down to 16 plus 25, which means that C squared is equal to 41. Now all I have to do is take the square root of both sides to find that C is equal to square root of 41. I did choose this problem on purpose because even though I have the sides A and B coming out to integers, it doesn't mean that my hypotenuse is always going to be an integer. Sometimes you get a number that isn't so nice, like the square root of 41. That doesn't mean you did anything wrong, it just means that, well, it just means that sometimes numbers aren't nice. For our next example, consider this triangle with a hypotenuse of length 5 and one of our sides of length 3. We have a missing side that isn't the hypotenuse, so the goal of our problem is to find that side, which I've labeled B. So the first thing I'll do is fill in the formula from the Pythagorean theorem with all the information I have. I have a hypotenuse of 5 and I have a side of 3. So I end up with the equation 5 squared equals to 3 squared plus b squared. One round of simplification gives me 25 equals to 9 plus b squared, at which point I just solve for b. When I do this, I get that b squared is equal to 16, which tells me that b itself is equal to 4. And we're done. We found our missing side. So we had two different kinds of applications of the Pythagorean theorem here. In the previous example, I had both short sides and I used it to solve for my hypotenuse. But in this example, I had one short side and the hypotenuse, but I can use that to backtrack sort of and solve for my missing side. In this next example, suppose that I have an isosceles triangle with a hypotenuse of 10. My goal is to find the length of the other sides. And it seems like I wouldn't be able to proceed because I only know one side, but the thing is I know this is an isosceles triangle, and isosceles triangles always have two sides of equal length by definition. And I know that none of my other sides are going to be equal to 10 because 10 is my longest side. So this tells me that my shorter sides have the same length, and I'll label those with x. Applying this information into the Pythagorean theorem, we get that 10 squared is equal to x squared plus x squared, which simplifies down to 100 is equal to 2x squared. Even though I have an x squared showing up, it doesn't mean that I have a super complex quadratic equation to solve, because at the end of the day, my lengths of the triangle have to end up being positive. So I can start by dividing both sides by 2 to get x squared is equal to 50, and then I can just take the square root of both sides to get that x is equal to the square root of 50. And the square root of 50 simplifies down to just 5 times the square root of 2. And we did this in another slide too. It's okay to take the square roots of both sides because I'll always end up with positive numbers because I'm dealing with the length of a side. Measurements are always positive. So in this situation, it's a well-defined strategy. These next examples will be a little bit different. I'm going to pose a triangle with particular side lengths without drawing it, and I'm going to ask whether or not it's a right triangle. The Pythagorean theorem can help us figure this out. On the first slide, we said that if I have a right triangle with sides labeled a, b, and c, c being the hypotenuse, then a squared plus b squared equals c squared. But the thing is, the theorem actually works in reverse. It means that if I have a triangle with sides a, b, and c, and I have the relation between these sides, a squared plus b squared equals c squared, it means that I am looking at a right triangle. The theorem works both ways, which is why it's pretty powerful. So, if I have a triangle with side lengths 6, 8, and 10, is it a right triangle? The most efficient way to use this theorem is to plug this information into the theorem itself and see if the equation balances. 10 is our longest side, so that's going to be a hypotenuse. So we need to check if 10 squared is equal to 6 squared plus 8 squared. Doing the math, we see that 100 is equal to 36 plus 64, so a triangle with side lengths 6, 8, and 10 is a right triangle. Now suppose that I'm looking at an equilateral triangle where every side has length 3. Again, we'll plug this into the Pythagorean theorem to see if the equation balances. We want to know if 3 squared is equal to 3 squared plus 3 squared. Well, upon inspection, we can see that's not going to happen, because 3 squared is equal to 9, and 3 squared plus 3 squared is equal to 18, and those are not the same. Therefore, this is not a right triangle. It actually turns out that no equilateral triangle, and by extension, no acute triangle, obeys the rules of the Pythagorean theorem. It's a theorem that only works for right triangles. And acute triangles only have angles less than 90 degrees.